So this first section is about what they're calling fundamental identities. I mean, it's all the same trig functions that you got to be proficient with for what we're being tested on. So actually, I mean, this is not bad stuff to be looking at this time. In fact, I'm sure, having gone through what this lesson is, there's going to be one or two answers on the test that are going to be flying by you right now if you're paying attention. Let's go. Okay, there we go. So by identity, trigonometric identity, identities are equations that are always true for all values of the variable. It's like when you solve an equation and you come up with something at the end, which is like 0 equals 0, right? That means it's always true, right? So it doesn't matter what you plug in for the variable, that statement's going to be true. Now, we learn about identities, which is really the focus of this chapter, because it helps us to solve equations, simplify expressions. And so it's broken out. There's 5 sections in the chapter. Right? This first one, we're using fundamental identities. The next one is when we do the verifying part. The verifying part is usually the part everybody remembers the most. But these 2 sections kind of go together quite a bit. When you verify the identities, you're using all these things you learned about in the first section. And then that sets us up to solve equations. So solving trig equations. Now, these 2 here are more identities. They're formulas, but they're identities. They help us to, simplify equations and expressions so that we can solve them. Okay. So the fundamental identities, I think there's like 4 slides here, which are just giving you these. They're in the book. I copied them here into 4 different parts. The first part, these are things we kind of already know. There's nothing new here. Right? Sine is 1 over the cosecant, and right under that they got cosecant is 1 over the sine. Okay. And same thing, cosine 1 over the secant, secant 1 over the cosine. Tangent 1 over the cotangent, cotangent 1 over the tangent. Right? They're all reciprocals of each other. And tangent can be broken down into the sine divided by the cosine. Cotangent would be cosine over sine, since they're flips of each other. But we will find it useful to do that. Sometimes you want to break it down, make everything sines and cosines. It'll help simplify. Blue, and 1. So I think these here should be very familiar. And you notice that I don't know what the reason is, but they tend to use the U for the angle in all these things. And you could just as well say theta or X or whatever. And sometimes they do in the problems. But in the identities, they always use U. Morgan? Good? Anybody? Allie? Are you okay? Right. The next, these are really important, right? Really, really, really important. The Pythagorean identities. And, where this comes from is Pythagorean theorem. If you, just for this one right here, let me do it over here. If you imagine on the unit circle, right, here's the angle U, the radius is 1, right? We know that across from the angle, that's the sine, and across and the adjacent to the angle, that's the cosine. And so just using Pythagorean theorem, sine squared plus cosine squared equals 1. That's what this one says right here. Sine squared plus cosine squared equals 1. That one should be as familiar to you as a squared plus b squared equals c squared, which I know you know from Pythagorean theorem. Okay. Now, if I start with this sine squared plus cosine squared equals 1. And I divide both sides by, I'm going to start with cosine squared, right? So if I divide this by cosine squared, and cosine squared, right? What is sine squared divided by cosine squared? What is sine over cosine? Please, you just copied it down. What is sine over cosine? Tangent, right? So sine squared over cosine squared and is tangent squared. And notice when you're saying that you're squaring, you put the 2 in between the tan and the u, or in between the sine and u. That really means like this, tan u squared. And that's what it means. But the notation is you put it right in between right there. Okay, what's cosine squared divided by cosine squared? 1. And if 1 over cosine is secant, then what's 1 over cosine squared? Secant squared u. That's this one right here. So this is just a reformulation of the first one. Like I said, you should know the sine squared plus cosine squared equals 1 easily, right? Now, if you're not sure about what goes where here or here, you can make them yourself easily enough. Like divide by cosine squared, you get this one. If you divide this by sine squared, you'll get this one, right? If I go sine squared over sine squared would be the 1. Cosine squared over sine squared would be the cotangent squared. 1 over the sine squared is cosecant squared. So you can figure these out yourself if you don't remember. I mean, I've often done that when I was a student. Just that was the only one I needed to remember. I can find the other 2 if I'm confused about it at all. Okay, now these identities are useful when you need to make a substitution that changes the function that you're dealing with, but you're going to have a squared function, right? All of these are squares. So if I wanted to change sine squareds to cosine squareds, then I could do that, right? I'd solve this for sine squared. That would be 1 minus cosine squared, and I'd plug in that. I'd substitute that. So the substitutions are, and you got to keep these, in your mind always. You can always jump from sine squared to cosine squared. You can jump from tan squared to secant squared. You can jump from cotangent squared to cosecant squared, just by making a simple substitution, if that's what you need to do. So these are probably the ones that you will use the most. I think the first slide, yeah, we use those kind of implicitly. They're always in there. Secant is 1 over the cosine, things like that. But these are definitely useful. All right. Now the cofunction identities are, as you can see, there's a sine pi over 2 minus u on one side, and there's a cosine u on the other. What did we say about the difference in the graphs of the sine and the cosine? They're just pi over 2 shifts of each other. Okay, that's all this is saying right here. All those graphs, sines and cosines are pi over 2 shifts. Tangent and cotangent, pi over 2 shift. Secant and cosecant, pi over 2 shift. I mean, you could verify, if you're not sure, for example, is that supposed to be sine of pi of u equals cosine of pi over 2 minus u? I mean, just do a substitution, right? If the angle is 0, then this would be the sine of pi over 2, which is 1. And then that would be the cosine of 0, which is 1. Right? If the angle was, if this u was pi over 2, then it'd be the sine of pi over 2 minus pi over 2, which is 0. And the sine of 0 is 0. And the cosine of 0 is, the cosine of pi over 2 is 0. So, I mean, you could figure this out if you were a little confused. We don't use these a lot. And to tell you the truth, when I think of these, I tend to think about these sum and difference formulas. Because in the end, these sum and difference formulas are going to be completely consistent with what we're seeing right here. You know, we could use the sum and difference formula to show that this equals the cosine of u. So we don't use those a ton, but that's where they come from. And we kind of know where they come from. I mean, they are pi over 2 shifts. We already saw that in the graphs. We've studied the graphs already. Then these are called the even and odd identities. There we talked about, we didn't do much with even and odd functions earlier in the class. Right? An even function is a function that, right, even function. F of negative x equals f of x, which means it doesn't matter if you go to the left or to the right, the same distance, you're going to get the same function value. And that there's two of these functions that are even, and they are cosine right? Because, you know, if I go pi over 2 to the left, I get a 0. If I go pi over 2 to the right, I get a 0. If I go pi to the right, I get negative 1. If I go pi to the left, I get a negative 1. F of negative x equals f of x. The other thing about an even function is they are symmetric with respect to the y-axis. So it looks like this function is the same on the left as it is on the right. Symmetric with respect to, WRT is with respect to y-axis. Right? An odd function f of negative x equals negative f of x. And if we look at the sign is an odd function. Okay, so sign goes like this. Oops, that was wrong. Right, the sign goes that's not a very good graph, but you know, if I go pi over 2 to the right, the sign is 1. If I go pi over 2 to the left, the sign is negative 1. That's what this is saying. F of negative x is the opposite of f of x. Right? F of negative x is the opposite of f of x. And that's called being symmetric with respect to the origin. And you know, one thing you could tell is if it is an odd function, it's got to go through the origin. It has to. Right? I mean that 0, 0 would definitely meet that right there. So every odd function goes through the origin. Every even function is symmetric with respect to the y-axis. So let's see. If cosine is even, which other of the 6 has to be even? The secant, 1 over the cosine. So the two even functions are cosine and secant. Right? These are the evens. All the rest are odd. And that's the way I remember it. Cosine, I know is symmetric with respect to the y-axis, therefore secant is, okay, and then all the rest is the other. And we don't have a lot of times that we make this substitution, but we do a few times. Good. Good. Okay, so there's going to be 7 examples here. Well, I think one of them's got 2 parts to it, but there'll be 8 examples then that we do. The homework is going to end up being the check, what do they call those? The checkpoints underneath. So it'll be 7 of those, or 8. So use the values of the secant and the tangent being greater than 0 to find the values of all 6 trig functions. The fact is, we know how to solve a problem like that based on what we've already done, in that if the secant is negative, then the cosine is negative. So this is telling us that cosine is negative and tangent is positive. Which quadrant are you in? Cosine is negative, tangent is positive. No, tangent is not positive in the second quadrant. The third quadrant, right? Cosine, which is to the left of the middle, is negative in that quadrant. And remember, tangent is sine over cosine. So since sine and cosine are negative in the third quadrant, tangent is positive. So you could draw the triangle here, just label a right triangle. It would be, hypotenuse would be 3, and the adjacent would be -2. Use Pythagorean theorem to find the third side. You could do it all like that. This is saying use those identities to do the same thing. So let's see. If the secant is -3/2, then what is the cosine? -2/3, right? That's the easy one. If the secant is that, then the secant squared is what? (9/4), right? If you're going to square the left, you square the right. You got 9/4. Okay, now we have an identity which involves tan squared and secant squared. And I don't have this. Let's see. Right there. 1 plus tan squared equals secant squared. So we can use that here. So that's going to be equal to 1 plus tan squared. So now we could solve that for the tangent. Right, so that'll be 9/4 minus 4, no, sorry, minus 1, or minus 4/4 is 5/4. 5/4 equals tan squared. So what is the tangent? What is the tangent? The square root of 5 divided by 2. Okay, now normally when you take the square root, you have to do plus or minus. Why do we not have to do the plus or minus on this one? Because it says the tangent is positive, right? So you don't worry about the minus. They told you that it's positive. Okay, so now we know the secant, we know the cosine, we know the tangent. Okay, if the tangent is that, what's the cotangent? Flip this, right? 2 over the square root of 5. And that will be 2 root 5 over 5. And let's see, how could we find the sine? That's the only one we don't know, right? Well, we don't know the sine and the cosecant, but we can find either way now. We've got a cotangent, which would give us a cosecant, or we could use a cosine to get a sine. How about that? Let's go. Cosine squared is 4/9. And then what's the substitution for cosine squared? Right, here it is. Sine squared plus cosine squared equals 1. So cosine squared equals 1 minus sine squared. Right, you're going to just take this and rearrange it. Cosine squared is 1 minus sine squared. Sine squared is 1 minus cosine squared. Whatever the substitution is, that's what you do. So here we go. So this is 1 minus sine squared. Subtract 1 from both sides. Negative 5/9. No, that's wrong. No, that's right. No, that's wrong. What is it? Minus 9/9, which is negative 5. Okay. And so that tells us that sine squared equals 5/9. So the sine is the square root of 5 over 9, or is it? Oh, sorry, over 3. Over 3. But again, when you take the square root, you're going to do plus or minus. And in this case, is it plus or is it minus? It's in the third quadrant. Is it plus or is it minus? It's minus, right? And then the last one is cosecant. So cosecant will be the flip of that. I'm just going to do it in one step, right? Negative 3 times the square root of 5 over 5. I would never ask you to use identities to do that. That I would personally, I would have drawn a triangle. I could have had this done so much more easily just by drawing a triangle. But they did this in section 4-ish. That was part of it, but I skipped over it then. I knew we'd have to do a little bit of it here. But again, this is something we could do without the identities, but you can also do it with the identities. Okay, simplifying an expression. So a lot of what we do here, besides applying the identities, is just applying basic algebra. I mean, you got to be able to look at this stuff as algebraic expressions of some kind. Like if I had to simplify this one right here, there's two terms. Is there a common factor? The sine of x. So you factor out the common factor, right? This is just greatest common factor factoring. This time, it's a trig function, right? This will be sine x times cosine squared x minus 1. And then you should be looking at that cosine squared saying, you know, I could substitute for cosine squared and make it as sine squared, and then I'll have all sines. That would certainly be more simple than having two different trig functions. Right, what's the substitution for cosine squared? Remember, this is the identity. Sine squared u plus cosine squared u equals 1. So if I want to substitute for the cosine squared, it is 1 minus sine squared, right? Cosine squared is 1 minus sine squared. So if I substitute here, sine x equals 1 minus sine squared x minus 1. And then the 1 minus 1 cancels. And then what do you think is sine times sine squared? Sine to the third, right? This is sine times sine. Now it's sine times sine times sine. So again, how do you think you would write that? With a 3 in between the sine and the x. Sine to the third. So there's a lot of factoring that goes on with this stuff. Again, we've seen so far in the two problems, we've used the Pythagorean identities on both. We used it multiple times on the first one, and we just used it once here. Okay. Factor. Now they even say simplify. They just said factor. Factor. Okay. Well, what is the in this letter A? What is the pattern you see there? Something that had a formula for factoring it. That's a square. Is that a square? Is 1 Could 1 be represented as a square? So what is this? What do you call subtraction? Do I have to do everything here? The difference of squares, right? It's the difference of squares. Remember the difference of squares, which we should not have to review at this point. A plus B times A minus B. So let's say I write this as secant squared theta minus 1 squared. How does that factor? Secant theta plus 1 times secant theta minus 1. Right, you got to look for those patterns. That is what should be the easiest kind of factoring problem, difference of squares. Certainly the people who made the textbook thought that's what they're giving you here. They weren't trying to trick you. Okay. Now, in the second one, we've seen this a little bit. We saw this a little bit when we did exponentials and logarithms, which was you can have an equation like this that is what they would call a quadratic type. And it's quadratic type because it's something squared plus something to the first power plus a constant. So it should factor just like if this was 4x squared plus x minus 3. I mean, if you can factor that, then you're going to do the same thing here. Exactly the same thing. How would we have factored a polynomial like that? Because it has a does not equal 1, you're going to have to go through some steps, if you remember. 4 times negative 3 is negative 12. What are the factors of negative 12 that add up to 1? Negative 3, positive 4, right? So we split up the middle term. 4x squared minus 3x plus 4x minus 3. Then we group the first two terms. We group the last two terms. We factor. If there's any factoring to do, there always is in the first set of parentheses. What's the common factor? Just an x. X times 4x minus 3 plus 4x minus 3. So this is x plus 1 times 4x minus 3. Well, we don't have x. In what we're actually factoring, we don't have an x. We have a tan theta. So this thing will factor as tan theta plus 1 times 4 tan theta minus 3. Right? Exactly this, just in place of the x, put a tan theta. You know, in the third section, when we're solving equations, very likely we'll get a problem like this, which is all of this equals 0. And then you'll have to, you know, if that's 0, then use 0 product property. You know, that means that one of these has to be 0. That gives you like 2 more equations to solve. So remember factoring. Okay, could we do factoring on this one? Cosecant squared minus cotangent x minus 3. What do you think? Well, not right away, because they're actually not the same trig function. Right? I mean, imagine that if you had, you know, you had parentheses, and the first term in each set of parentheses was cosecant, right? So that when you multiplied them together, you got cosecant squared. How is it that the middle term would be a cotangent? I mean, that's a problem. So we need to make this a trig function, or an expression which only has one trig function. Okay, well, I've got cosecant squared, and I got a cotangent. we go back to our identities here, there you go, Pythagorean identity. That's a substitution that we can use to go from cosecant squared to cotangent squared. And then it'll all be in terms of the same trig function. So definitely you want to do that. So 1 plus cotangent squared equals cosecant squared. Right, so this will be, 1 plus cotangent squared u equals cosecant squared u. We're going to substitute that right there. So that'll look like this. 1 plus cotangent squared u minus cotangent of u minus 3. I just replaced the cosecant squared with 1 plus cotangent squared. Okay, now let's simplify. Cotangent squared u minus cotangent minus 2. Okay, now we can factor it. And this should be an easier factor. You know, what are the factors of negative 2 that add up to negative 1? Negative 2, positive 1, right? So it'll be a minus 2 here. There'll be a minus 2 here and a plus 1 there. What is the first term in parentheses? Cotangent of u, right? Cotangent u. Cotangent u. So this part here, you got to think. You always want it to be one trig function, and if you've got a square, we don't have a substitution for the cotangent, right? We only have the substitutions for the squares. That's why you got to see: is there something that would get me from the cosecant squared to the cotangent squared? Yes, Pythagorean. Trying to think. That's number 4. We didn't have to make a substitution. Yeah, this one we had to make a substitution, Pythagorean. Or no, we didn't. We just factored on that one. The one before we did, that was 2. So 3 out of the first 4 we've used as Pythagorean substitutions. 5. Simplify a trigonometric expression. All right. Do we see any common factors? Sine t, cotangent t, cosine t. No. T is not a factor. T is the argument of a trig function. It's not a multiply that goes on in between there. Okay. So here, and this is a kind of a common thing that you end up doing sometimes, is break it down into sines and cosines. Right? This is already a sine, that's already a cosine. The cotangent is, by the first identities, what's the cotangent? In terms of sines and cosines. It's cosine over sine, so substitute. Sine t plus cosine t over sine t times cosine of t, which is sine t plus cosine squared t over sine t. Okay, so we've got, essentially we have a fraction and we have not a fraction, but if we want to add them up, we need a common denominator. How do I find a common denominator between these two? Divide by sine t. No. How do I make the common denominator will be sine t. How do I make this one have a denominator of sine t? You multiply by sine t divided by sine t, right? Arithmetic, not even algebra. So now this is sine squared t over sine t plus cosine squared t over sine t. Again, more arithmetic. How do you add fractions when they already have the same denominator? Just add the numerator. So that's sine squared t plus cosine squared t over sine t. But we have a substitution for sine squared plus cosine squared. What is sine squared plus cosine squared? 1 is 1, right? So we can that's another substitution with Pythagorean identities. That is 1 over the sine of t, right? This is the same as this. And then 1 over sine t, we have a substitution for that. It's cosecant. So this whole thing can be simplified as the cosecant of t. Okay, adding expressions. Again, these two fractions, how am I going to add them up? What do I need to do to add them up? Their common denominator, right? Well, what would be the common denominator between 1 plus cosine in this fraction and sine in this fraction? How about the least common denominator will be 1 plus cosine times the sine. Right? You can always just multiply the two together. This is one factor. I shouldn't have done that. Oh, that was wrong. I'll have to make that work. Oh, that's, darn it. Now, unintended consequences. Okay, white, big. There we go. So I can't do that. Or I have to be careful about that. I think I can get a little bigger now. Okay, so we need to multiply, in order to have the common denominator, we got to multiply this one by sine over sine. And we're going to multiply this one by 1 plus cosine over 1 plus cosine. So now they have the same denominator. Add the numerators. Right, this will be sine squared plus cosine theta plus cosine squared theta divided by sine theta 1 plus cosine theta. Okay, how could I simplify the numerator? Sine squared plus cosine squared is 1, right? So these two, actually, we can replace with a 1. So now we've got 1 plus cosine theta in the numerator divided by sine theta 1 plus cosine theta. Okay, and then because we have a common factor in the numerator and denominator, we can cancel it. So we have 1 over sine theta. Well, that's what that other one simplified to also, right? So 1 over sine is cosecant. Good. Okay, so rewrite 1 over 1 plus sine x so that it's not in fractional form. And something I've never noticed before is that in the book, they have this symbol right here. And I'm pretty sure what that means is that there's a calculus connection here. Not that we're using calculus here, but that in calculus, you're going to find the need to do this thing, right? That this is something that we would have a hard time specifically doing what this symbol represents in calculus, which is called an integral. So we would try to rewrite it so that it does not have, I mean, a lot of times what they say is don't have a binomial denominator like that. They didn't say that, actually. They said make sure that it's not in fractional form. Okay, let's see what we do with that. And I think I've got this on the next slide, too. So here's the strategy in order to get rid of a binomial denominator. And that is you multiply by, if that's 1 plus sign, then you multiply by 1 minus sign. It's kind of like multiplying by a conjugate, right? So 1 minus sine x, 1 minus sine x. Now notice what happens when we do that. In the numerator, we just have 1 minus sine x. In the denominator, this is the factoring of a difference of squares, right? 1 plus sine times 1 minus sine. So this is 1 minus sine squared x. And there's a lot of that, you know, because the Pythagorean identities are so useful, and they're all squares, and they've all got a 1 in there somewhere too, that you can often make a difference of squares. And either factor we're using it or go backwards. You do have the factoring of it, and then you go back to this. And now we can use Pythagorean identity. What is 1 minus sine squared? It's cosine squared, right? If sine squared plus cosine squared equals 1, then 1 minus sine squared is cosine squared. So this is 1 minus sine x divided by cosine squared x. Okay, well, we're still not where they said we had to be. They said these should not be fractions anymore, and that's still a fraction. So here's what you do. Split it up into 2 terms. You got one denominator under 2 terms in the numerator. Make it 1 over cosine squared minus sine x over cosine squared. Now, the 1 over cosine squared, you could deal with that right away, right? What is 1 over cosine squared? 1 over cosine is secant, so that's secant squared. So that's the first term. Secant squared x. Now this is it's a little bit of a problem because you got a sine in the numerator and you got cosine squared in the denominator. But if you break off this cosine squared, write it like this: sine x over cosine x times 1 over cosine x. Right, there's your cosine squared. And then the first sine x over cosine x is tangent, and 1 over cosine x, secant. There you go. Okay, now it doesn't have a denominator. Good. So when we get to the next section, which will be next week, and we're verifying trig identities, you could see, especially if you get to like number 2 in this list of, it's called guidelines, look for opportunities to factor an expression, add fractions, square a binomial, or create a monomial denominator. Those are all things that we just did in that first section. And look for opportunities to use fundamental identities. Okay. Number 4, if anything you did up here doesn't work, turn everything into sines and cosines. Okay, we did that one too. Right. So that all that everything we did there we'll use in the second section. So that is that. We still have 40 minutes to go. The homework, underneath every one of the examples, the 7 that I did, there was a checkpoint, which is very similar to the example, which I just did there and which is also in the book. So that's it. Due next, what is today? Tuesday, next Tuesday, right? Next class we'll have the test, and right now, if you want to study for the test, if you got questions, I'll help you out. Just be prepared for Friday.